So how did the last tests go? We all know that. Today we're going to take a sample from a population. We're going to use an average from the sample to estimate the average of the population. And we're going to pretend this population is very, very small. A 4-person class. All right? 4-person class. And there's the grades. 60, 70, 80, 90. Okay? Obviously I have bigger classes than that. However, we're going to keep it small for a reason. All right? We'll get to that in a minute. So if I make a dot plot of the population distribution of all the grades made, what am I doing? I'm just putting a dot at 60, 70, 80, 90, right? Nothing hard about that. Now, number 2 says take a sample of any of the 2 scores. Which 2 scores do you want to use as our sample?
70.
Okay, I heard 70 and 80. So if we add those, the mean of the sample would be, what, 150 divided by 2? Or 75, right? When we take in the mean from just a sample, a subset of the population, we use this symbol X bar. We talked about X bar? I don't think we have in here yet. Or have we? Have we? Yeah, we have. Okay. Figure out all the possible samples of size 2. This is why we have a small population. All right. So if I have 4 things, okay, so I could choose sample of size 2. There's going to be 6 of them. So the first sample of size 2 would be 60 and 70. And I want to find the sample mean for that subset. So the X bar here would be what? 65. Sample of size 2, 60 and 80. Add those up, you get 140. Divide by 2, you get 70. And then 60, 90. If I add those up, I get 150. Divide by 2, you get 75. Next one would be the 70, 80 we just did, right? And we found that that has an X bar of 75. Then I would go 70, 90. What's the X bar of those 2?
80.
And then what's next? 80 and 90. Add those, I get 170. 85. All right. Everybody see what we did? We took 2 out of the population, averaged them, that creates the X bars. Now, coming back up here for a second, this is the population, right? For the population mean, looking at those 4, what would the average of those 4 be? Just looking at the dot plot, where would it average out to be? 75, right? All right, just keeping that as food for thought in a minute. Now we're going to make a dot plot of what all the X bars. Okay, so we had an X bar at 65, at 70, 75, 80, and 85. Now keep in mind, each dot here is an X bar, right? From a sample of size 2, right? It's an X bar. It's not one individual grade, it's the average of 2 grades, right? So if I now look at this and I say, okay, what is the mean of all my X bars, where would they average out to be?
75.
Everybody agree it averages out to 75? All right. And then it says, what's the mean of the whole population? Well, it's 75, isn't it? That's what we saw up here. And then what we just did is take a sampling distribution. We took all the samples of size 2 possible, found the means of those samples, and made a distribution of the sample means. It's a lot of words. Did y'all get that? Yeah. These are sample means, not individuals anymore. Sample means. The distribution of the sample means averages to be the same as the population that we knew it would be. All right? Now, reality is, when we have a big population, we're not going to know the average, right? And we don't want to do all the work to find it. We want to be able to take a bunch of samples, get the average of those samples, and see where they line up if I did a distribution. And what we're going to find is that the mean of the population is equal to the mean of the samples taken. The true mean of the population is going to be equal to the sample means, the mean of the sample means. It's a mouthful. You following this? It's a lot for a Monday after a break, okay? So this is kind of our shortcut. Instead of having to get every individual in the population and average them, we just take we take a bunch of samples. And in this example, we took every possible example of size 2, right? Reality is 99% of the time, you're not going to take every possible sample of size 2. Like, think about it. If I wanted to know something about the average of the senior class of this school, every possible sample of size 2, how many samples would that be? It would be more than even the number of students, wouldn't it? So it's not realistic to get every sample, but if I get a whole bunch, won't I be able to begin to see a pattern? Yes, and that's the idea of a sampling distribution. So, go back over here. I want you to notice something. Look at the spacing here. This goes from 60 to 90, the population does, doesn't it? What happened when I went down to samples? The spread got a lot smaller, didn't it? All right, and that's going to be true every time you do it. When you take a subset, you're taking a sample, which is going to decrease that variability. Well, the benefit of that means it's even closer to the truth, right? There's less variation. So we're getting lots of vocab here just to start the chapter, right? Doesn't continue like this, but alrighty, so I'm pretty sure I do this in the video, but I'll just do it for now. You haven't watched the video yet. So here's the population, right? Big population we're interested in. And we already said we don't want to do all the work to survey every individual in that population, so we're going to take a subset, a sample, right? And we're going to use the sample then to make decisions or inferences about the population. So we're going to take a good sample, a random sample, not biased as much as we can control it, so that whatever the sample tells us, we're going to make that conclusion about population, right? Now, a couple words you got to know is a parameter and a statistic. It has to do with the measurement, whatever measurement we're interested in here, and usually it's just averages and percentages, okay? So sometimes standard deviation, but here we go. A parameter is the number that describes the population. And usually it's what we're going to be estimating. All right? The statistic is the number describing the sample. You're like, what the heck? What is the difference? Well, if I take the mean of every individual in here, that would be the parameter of the population. But if I take the mean just from the sample, that represents just the sample, right? So we call it a statistic. All right? Now, to save us some wording, we give some shorthand. So we have special notation for these things. Okay, some of this you already know. Like if it's the mean, the parameter gets the mu, the curly m. The statistic is x bar. When you see x bar, you know that's an average from just a sample, not the whole population. Proportions, what are proportions? It's just a rate, right? A percentage. It's a fancy word for percent. So if it's a percentage, I want to know the percentage of blondes and whatever. If it's from the if it represents the population, we use P. If the percentage only came from a sample, it's P hat. And then SD, standard deviation. Sometimes we do this, sometimes we don't, but just so you know, standard deviation, the parameter symbol is sigma. And if it's a statistic, it's just S sub x. So the parameters are all Greek letters. The P is actually the Greek letter rho, but it looks like a P, so it's just easier. Whatever. The parameters are all Greek letters. The statistics are all letters with hats on them or something, right? A bar, a hat, or a subscript. All right. So that's how you know where this information is coming from. Now, get this guy. I don't know where to go with that. All right, open right there. A sampling distribution. It shows the statistic found in all possible samples of size n. All the possible samples of size n. So even if I give you a distribution and say I took 300 samples of size whatever from this population, is it truly a sampling distribution? No, because I don't have every possible sample. That's just highly unlikely it's complete. All right? It gives us a good idea, but it's not necessarily complete. All right? Unbiased estimator. We use the sampling distribution because it gives us an unbiased estimator of the truth. Remember, we don't really know what the population mean is. We're trying to estimate it. So we want to use something that's going to give us a good estimate, because a bad estimate's worthless, right? We want a good one, so we want unbiased estimators. So we say it's unbiased if the mean of the sampling distribution is equal to the actual parameter we're interested in. So if we take a whole bunch of samples, put them on a dot plot, whatever, and we find the mean of all those samples, that mean will be equal to the truth that we're trying to find. Now, just for funsies, better estimate. So when increasing the sample size, the sampling distribution variability will decrease. It will always decrease. Increasing sample size will decrease variability. You will use that truth from here on out. All right? Now, here's our application. The James family has 5 children: Jocelyn, Elise, Michael, Erica, and Sarah. Complete the table by listing all 10 possible samples of size 2. This is kind of tedious, but it's the last time I think you have to do it. Calculate the sample mean for each sample. The first column is completed for you. So in the first column, they did Jocelyn and Elise. So what is that, 6 and 8? Oh, 8 and 8, sorry. Of course they picked the easiest one. So what's the average of 8 and 8? It's 8. There you go. So my next sample would be Jocelyn is 8, Michael is 14. So add them up, you get 22. What's the average? 11. Good. Okay. Next would be Jocelyn and Erica. So 8 and 16 is 24 divided by 2 gives me a 12. Jocelyn and Sarah, 8 and 18 would be 26 divided by 2 is 13. Next would be Elise and Michael. 8 and 14 is 22 divided by 2 is 11. Elise and Erica.
For Elise, because they're both 8.
But I'm just doing Elise and Michael and then Elise and Erica. I don't have that combination yet.
They're all the same.
Elise is also 8.
Oh, I see what you're saying. Yeah. So this will be 12. Is that what you're saying?
Yeah.
Okay. Y'all are just ahead of me. All right. Elise and Sarah is going to be 13. Then what's next? Michael and Erica. Well, that's 30. That's going to be different, right?
Mm-hmm.
Michael and Sarah. 14 and 18 is 32. So that's 16. And then lastly is Erica and Sarah. So 16 and 18 would be 34. So average would be 17. All right. Create a sampling distribution of the sample mean age of samples of size 2. How many times can you put sample in a sentence, right? So confusing. The wording is so confusing. I'm with you on that. First time I heard this, I was like, what just happened? All right, so I'm doing a dot plot. I only needed to go from 8 to what, 17? Okay, ages, and I would put samples of size 2. I would say average age for samples of size 2. So you want to label it like always, right? And then I'm going to put dots based on our calculation. So we had 8, 11, 12, 13, 11, 12, 13, 15, 16, 17. All right, somebody got a calculator handy? Everybody have one out already? No? Cool. So I need somebody to find the mean of the sampling distribution. So the mean of all my X bars that we calculated. Somebody, who's going to do that one? I got no volunteers, got nothing. You got it, Caitlin? Oh, okay. So the mean of the sampling distribution, so the mean of the X bars you got was 12.8? All right, what about the mean of the true population? The actual ages. So would that be what? 8, 8, 14, 16, 18? Yeah, I get 12.8. Yeah? Yeah, confirmed? All right. Is the sample mean an unbiased estimator of the population? Is it the same? Yeah, that's all it's saying. Is it the same as the population? Yes. And how do you justify it? You show it numerically. So yes. That's because the mean of all my X bars is equal to the true mean. That's what unbiased estimator actually means. Okay? I have my work right here. If I didn't have my work, I would show it. All right? Now, suppose now we had taken samples of size 3 instead of samples of size 2. Would the variability of the sampling distribution of the sample mean be larger, smaller, or the same? We're just talking about the variability here.
The variability would be smaller.
The variability, the spread of all my dots would be shrunk down a little bit, right? Because my sample size went up. With me? All right, it would be variability would be smaller because my sample size increased.